Hi guys. So, moving on with our whole idea about parallelograms. In fact, now we're moving backwards. Yesterday we learned all the theorems that pertain to what happens with angles and sides and diagonals if something is a parallelogram. Today, basically, we're going to look at quadrilaterals and try and decide if they are a parallelogram. Okay, I said that weird. Yesterday we said, okay, if you got a parallelogram, then this happens with the sides and the angles and the diagonals. Today we're going to go backwards. If we got a quadrilateral and we see this happening with sides and angles and diagonals, can we tell that it's a parallelogram? Basically, we're moving backwards from everything we did yesterday, okay? So the converses of the theorems from yesterday are going to prove that a given quadrilateral is a parallelogram. So let's get started right away. Basically, I'm going to throw a whole bunch of theorems at you that go backwards from what we were doing yesterday, and then I'm just going to give you some examples of how we use them in some problems. All right? So start right here with a little definition. This actually was the same slide we had yesterday, just to remind you what's a parallelogram, what are opposite sides, opposite angles, and consecutive angles. Hopefully you already feel comfortable with this. But next, Theorem 6.8, which is the converse of Theorem 6.3. Remember yesterday Theorem 6.3 said if something is a parallelogram, then its opposite sides are congruent. Well, today we're going backwards. If a quadrilateral has opposite sides that are congruent, both pairs, both sets, then it must be a parallelogram. Okay? Next, again, the converse of 6.4, we'll call it Theorem 6.9. If an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. In other words, if I take angle B, for example, and if it adds up to 180 with both A and C, okay, if it adds up to if B adds up with A and C, both of them to make 180, then the quadrilateral is a parallelogram. Okay, and I could have chosen any other angle besides B. Okay, I just used one example of B, but if A adds up with B and D to make 180, you got a parallelogram. Same kind of thing with C, same kind of thing with D. Okay, if any one of these angles adds up with both of its neighbors to make 180, then it's got to be a parallelogram. Okay, so next, converse of 6.5. If a quadrilateral has both pairs of opposite angles being congruent, A is congruent to C, B is congruent to D. If that's true, we must have a parallelogram. Okay. Next, if the diagonals of a quadrilateral bisect each other, then that quadrilateral must be a parallelogram. Okay, so again, every one of these was the converse of something we learned yesterday. Yesterday we said if it's a parallelogram, then this must be true. All right, today we're saying if this is true, this must be a parallelogram. Got it? Got it. Okay, Theorem 6.12. This one's new. This is not a converse of one we learned yesterday, but it is kind of interesting. If one pair, I should take out that typo. If one pair of opposite sides is both parallel, right? There's our little parallel mark, and congruent, then it must be a parallelogram. If one pair of opposite sides is both parallel and congruent, it must be a parallelogram. Theorem 6.12. Okay, so here's a little summary. I pulled this straight out of the book. You might want to have that written down and handy and available to you, though. So if we're ever asked to prove that a quadrilateral is a parallelogram, we have several ideas that we can use. So if we're looking at a picture of a quadrilateral and we see that it is marked in such a way that, all right, I'm seeing both pairs of sides are parallel, well, we know it must be a parallelogram because that's the definition of a parallelogram. If I see that both pair of sides is congruent, then by Theorem 6.8, it must be a parallelogram. If I see that one angle adds up with both of its neighbors to make 180, Theorem 6.9 tells us that must be a parallelogram. Okay, same thing with opposite angles, same thing with bisected diagonals, and by 6.12, opposite sides are both parallel and congruent, we must have parallelograms. So in all these cases, we can look at any of these figures or any of these ideas and say, okay, if it meets these conditions, then these are the reasons why this or this or this or this or this or this must be a parallelogram. Okay, so how do we use them? Again, I'm not going to rattle through a whole lot here. I'm going to let you pause and follow through if you need, but the explanations will go through fairly quick, okay? So pause all of these next slides and go when you're ready. Okay, here we go. For what value of y must this be a parallelogram? Okay, well, to be a parallelogram, according to theorem 6.8, both pairs of opposite sides must be congruent. So I'm going to start up here that this must be congruent to that because I can solve that puppy, okay? So by doing algebra on it, subtract the x, add the 5, we find out x is 6. And if that's the case, then we can also remember the second part of our deal is that both pairs of opposite sides must be congruent. So I set this equal to each other, I plug in the 6, and I find out that y would have to be 8. Next one. This is the one I hated. Not because it's a really good problem, but because I took a wrong avenue. And I just want to point out to you, this is one of those examples, guys, where you got to try something, and if it works, cool. If it doesn't work, try something else, okay? No reason ever to not try a problem, because it happens to the best of us, okay? So what value of y must KLMN be a parallelogram? All right, so my original thought, check this out, was, all right, to use theorem 610, both pairs of opposite angles must be congruent. So I thought, well, here we go. I know how to do this. Both pairs of opposite angles, this must equal this, and this must equal this by theorem 610. So I figured, all right, we're ready to go on this. Let's continue on. We got a system of equations, all right? So this one looked like it was easy to get y by itself, so I could do substitution. Then I did the substitution, and I got right there. And when I looked at this, I'm like, shucks. I got the same thing there. That means it could happen with any number. Darn. We have an equation that we can't use. Need to try another approach. So, with my next approach, which is all over here, and it's a little more red writing because I got to explain it a little more. But my thought was that, okay, so my first thought didn't work. But my second thought, try theorem 6.9. Okay, it says that a quadrilateral is a parallelogram if an angle is supplementary to both of its consecutive angles. Okay, so if I'm going to use that one, it means this plus this must equal 180. There's one of my equations that I could use. It also means that this plus this must equal 180. Second equation, right? You with me? So, and I got a couple other equations I can write from there. I know 12x plus 7 and 4x plus 13 must be 180. All right, if all of these sets, there's my fourth one, 4x plus 13 and 3y plus 2. So, there are four possible equations that all have to be true, considering theorem 6.9, that to be a parallelogram, any one angle must add up to 180 with both of its neighbors, right? So here's our four possible equations. Now I got really happy here because I noticed that this equation right there and this one right there, we can solve those without even using a system of equations, right? So taking the first equation, simplifying and solving, y is 43. Taking the third equation, simplify, we solve, find x equals 10. You can follow the algebra. I went and plugged these values back in, and I found out that these guys end up being both 53 degrees. That one there and that one there. And these other two end up being 127. And boy, that just makes perfect sense because the opposite angles are definitely congruent, and the consecutive angles definitely add up to 180, we got ourselves a parallelogram. All right. Next set. For what value must y of y must KLMN be a parallelogram? Pause. What are you going to use? Which of those theorems? Here we go. I'm choosing theorem 611 about the diagonals must bisect each other, which means that LO is congruent to ON, or 2x must equal 4, or x is 2. Also, it means that KO, oh, that's pretty, must equal MO, or right here, when you're going to solve that, you're going to find out y is going to equal 6. Let me put that back so you can see it all. Okay, diagonals of a parallelogram must bisect each other. These must be equal, as well as these two must be equal. Okay, next, can we prove? Now, going back, we're not going to do a whole lot of detailed proofs, but can we look at this and prove that it's a parallelogram? Pause. Answer coming shortly. Here we go. Yep, we can. Since the same side interior angles add up to 180, then DE and GF must be parallel because, we remember, we got the converse of the same side interior angle theorem. If these add up to 180, then these two lines must be parallel. Good? Good. All right. So, we know those lines are parallel by the converse of the same side interior angles theorem. Also, those sides are congruent. Therefore, by theorem 612, opposite sides are both parallel and congruent. We must have a parallelogram. Can we prove this one's a parallelogram? Pause. Answer coming. Nope. We got nothing that tells us about consecutive sides being congruent. Only opposite sides. Okay, none of our theorems involve consecutive sides. Only they involve opposite sides. Next, can we prove this is a parallelogram? Answer coming. Here we go. Nope. Not without knowing something about opposite sides being both congruent and parallel. I don't have both of those sets of knowledge for any of the opposite sides. And this one? Here we go. Answer coming. Yes. Okay. We've got parallel lines. I didn't want to do that. I want to do this. Parallel line, transversal, alternate interior angles here and here. So since those are congruent, DE and GF must be also congruent, or also parallel. Looking at these lines here, cut by this transversal, if this angle and this angle are congruent, then DG and EF must be parallel. And if both of those two are true, if these are parallel and these are parallel, all right? So, by the definition of a parallelogram, we must have a parallelogram if both opposite sides, both sets of opposite sides are congruent. And the alternate interior angles theorem tells us that they are both opposite pairs of sides are parallel. And the alternate interior angles theorem tells us that this is true. All right, done for today. I will see you next time. Have a good one.